Salatu salam ala Rasulillah. Ladies and gentlemen, good morning. My talk is about analysis of brilliant green dimaterial-based organic heterojunction using dielectric response and impedance. I am Mostafa Ben Hadi Dibab from researcher in and head of FDFCA research group, University of Science and Technology Oran. Oran is a city, Sagat city in Algeria. It is located at the west of Algeria, seaside. This is the second university. We have two campuses. This is the big campus. To follow me, you have my research guide, my Scholar, Google, ORCID, and on LinkedIn. The outlines are the partner and co-author introduction that I used in microelectronic organic electronics, famous techniques of film deposition, chemistry of brilliant green, experimental protocol, various characterization, the electric response, and we ended with a conclusion. These are some partner and co-author. At the left, Dr. Youssef Ojak from Turkey, and Dr. Aisha Mariam from Kadir Mahiddin College, Tamil, India, Professor Ozilik from Gazi University, Turkey, Dr. Kalili from Demirel University, Turkey, Professor Aydogan from Erzurum University, Turkey, Professor Yahshi from Marmara University, Istanbul, and Professor Ben Ahmed from Sfakas University. Introduction. Organic materials have been used as alternative candidates to inorganic ones because of their K properties, including low cost, high thermal and chemical stability, and ease of device fabrication in modern industry. Organic molecules can be used in many different ways. For instance, electrical and photoelectrical properties of metal semiconductor MS devices utilizing a thin organic interface layer have been previously studied as photovoltaic cells, photodiode, and Schottky diode by a major number of authors. The organic molecules have been previously used for the electrical device fabrication such as pentacene or poly 2-methoxy-ethyl hexoxyphenylvenin on PSE and PNIO on N-polyadenine on NSE Schottky diode. In order to make organic thin films, various deposition routes are already used, like spray pyrolysis and spin coating. Organic semiconductor, OSC, offers several advantages like a lightweight for practical portability and flexibility, leading to less fragile than organic semiconductor, which must be deposited on flat and unbending substrates. Organic semiconductors are commonly easy and conservative to be created in the research facility. Although OCS-based devices have certain restrictions, like the lifespan of organic display device is shorter than that of traditional liquid crystal display LCD. OCS meet the applications such as the rate used in the field of optoelectronic for development of organic light-emitting diode, OLED, and device competing with LCD, the matrix of red, green, and blue, easy manufactured either by vacuum evaporation procedure or utilizing the inject printing. Organic dyes have been used as an active part of various electronic devices, including dye-sensitive solar cells, DSSC, heterojunction, biosensor. Brilliant green BG have been this formula, C27, H34, and 204 and S chemical formula is characterized as one of the color of 3-methane used to color silk and wool. It has been used to adsorption and photocatalytic behavior of various materials, including metal oxide, chalcogenide, and boron-doped diamond under light. The BG films are deposited by spin coating technique on a P-type silicon substrate The gold front contact is evaporated at pressure 10 to the power minus 6 store on BG, PS, P-type silicon structure. We achieve the electrical characteristic of the organic diode-based BG die. Organic materials, Shanks, and thermoionic methods are programmed to extract the electrical parameters such as ideality factor, the resistance RS, the barrier height from the current voltage characteristic, and their dark and room temperature environments. The capacitance voltage, CV, and conductance voltage, GV, for several frequencies are measured, making it possible to evaluate the carrier concentration, diffusion, potential, barrier height, and density interface. The effect of light on current voltage characteristic is demonstrated to determine the photovoltaic properties of the fabricated diode. We pass now to the die used in microelectronic, organic electronic. We have bright green of this work, and the reference is displayed. We can have also bright blue. We can have also blackberry juice for the dye-sensitive solar cells. We can have also beta-carotene, and some of the work are on carbazole-based dyes. Famous techniques of thin films growth and diode fabrication. We have a lot of several techniques, and I resume the main ones, which are spin and deep coating, which are chemical techniques. These techniques do not need vacuum, without vacuum, easy methods. Second, spray pyrolysis is a chemical technique without vacuum also, but needs time and space saving. And in the third, we have radio frequency sputtering and thermal evaporation, which are physical techniques which need vacuum. Fabrication needs more time and obstructive equipment. In this slide, we demonstrate a chemistry of Bryant green. Bryant green, also known as Zelenka, is one of the trialmethane dyes. It is closely related to the malachite green, as Wikipedia. BG is an organic compound, specifically a synthetic organic dye. It is aniline based by belonging to the trialmethane group with this formula, chemical formula, with mass molar 482.64 gram per mole, melting point about 210 degrees Celsius. It is soluble in water, 100 gram per liter at 20 degrees Celsius. It is classified as a basic cationic dye, and it is organic hydrogen sulfide sol. It is also in various, used in various industries, including textile, paper printing, and leather dyeing. It is also has some medical application as antiseptic. At the right, we have the configuration or design of this molecule. Experimental setup. We have here getting highly quality electronic equipment required cleaning in order to remove the remaining grease and contaminants that have adhered to the substrate surface. The P-silicon P-type silicon wafer doped. The P-type silicon wafer doped with boron and having a resistivity of 1 to 10 ohm times centimeter are degreased in a boiling 3-chloroethylene solution for 5 minutes, then vibrated in acetone and methanol in an ultrasonic bath. In a hydrofluoric acid bath, the native oxide layer on the surface of silicon wafer are chemically erased. The procedure is finished right before the deposition to create a silicon surface that is hydrogen passivated, preventing the production of oxides while the substrate is being stored. Prior to making the device, the unpolished side of the silicon wafer is thermally evaporated in vacuum system at very high pressure using 200 nanometer high purity for an aluminum thick metals purchased from Kurt Lesser company. The metal is then annealed in a furnace at 420 degrees Celsius for 3 minutes to obtain low resistivity ohmic contact. The easy spin coating method is used in the production of the BG molecule-based device. We dilute 24 milligram of BG purchased from Sigma-Aldrich in 50 millimeters of methanol. BG thin films are applied to P silicon substrate using a spin coater, then spin for 5 minutes at velocity 2000 RPM. This thin film measurement yields a thickness of 673 nanometer at high frequency through capacitance voltage measurement. Next, a 1.5 millimeter diameter mask was used to evaporate high purity aluminum metal, resulting in 200 nanometer gold front contact with structure. Figure is displayed on the slide 23, depict the cross section of the gold on BG on PSE on AL heterostructure, which displayed the dye BG brilliant green chemical structure. Later, we make the electrical measurement of current voltage carried by Kate Lee 2040 100, and the equivalent HP impedance analyzer setup is used to measure the CV and the GV characteristic in dark and at room temperature. Some experimental details. We have the precursor mass, 24 milligram BG powder, diluent for 50 milliliter of methanol, deposition time for 5 minutes, mask radius 1.5 millimeter, substrate P silicon, and the contact gold. Preparation. Okay, here we can we display the different steps of preparation. In figure one, we have the spin coater, and 2, we have the preparation of the solution, and then we have in 3, we have a different step of cleaning by water, cleaning the substrate by water, by deionized water, by acetone, and then we dry it by nitrogen. Here in figure 1, we have hot plate to heating and stirring the solution. And in 2, we have the glove box to prepare. And in 3 and 4, we have fabricated the diodes. In this figure, we have in 1 the setup of thermal evaporator. And at right, we have the crucible. We use crucible sometimes to make annealing of the powder in the furnace, and we have the gold wire for the contacts. In this figure, we have fabricated samples at figure 1. We put the sample in the boats, a crystal glass boat. Sometimes we use alumina boats. And in the figure 2, we put them in the tubular cylinder and put it in the furnace. In this figure, we can explain the spin coater in 1, 2, thermal evaporator. 3, we have the contact gold. It's display the contact as the dots of gold. In 4, we have also the holder of substrate and substrate after evaporation. 5 and 6, we have some other contacts in aluminum. Here we have the RF sputtering. This is a system to fabricate good films. And at 2, we have the tubular for the annealing. Sometimes for also to prepare for some solar cell like CZTS, for example. Here we have the journey in lab. We have our brilliant green in this bottle, and we pass to the weighing mass and dilution, stirring, and obtaining the homogeneous solution. We pass now to the various characterization. This is the main setup to characterize the current voltage, is the Keitel model 2400. And in the second figure, we have the electrode to measure and to get this curve, okay? Current, we called the current voltage characteristic of a diode of solar cells, okay? Here we displayed another setup. This is, we called the solar cells simulator. We use it to get characteristic under lights, okay? Here we use only one lamp, so the wavelength is fixed, and we can here, here we have these solar cells, okay? This is the beam light is here. Here we can change the intensity, milliwatts per centimeter square. We can go from, for example, 20 to 100 or more. And here we have the box. We can use it. In this technique, we use measurement under light. And we can also stop the light and measure the current voltage in dark. Here another setup to measure, this is impedance meter to measure the CV at right here. And we can also measure the GB at room temperature. Here it is our heterostructure diagram design of the gold on BG, on PSC, on aluminum heterostructure diode, and chemical structure of diode is displayed at right. Here we have the aluminum back contact, the P-type silicon substrate, the BG organic here, and this the contact on gold. Here we have the lights, and here we have our Keitel measurements. We obtained this characteristic, current versus voltage. We have two parts here. This is negative voltage, we call the reverse voltage. This is the positive, we call forward voltage. We have in dark this curve in the black, and we have measured under three elimination intensities. We have this graph. So this model follow based on the thermionic emission model. The current can be expressed at this expression, current equal I0 exponential V minus ERS and KT, where E and V are the experimental current and applied biasing voltage of the BG device, respectively. E0 is the reverse saturation current, can be written versus the area of contact of Richardson coefficient, temperature, and electron charge, Boltzmann coefficient, temperature, and barrier height, where the effective device is selected as the value is this 0.071 centimeter square. And Richardson for the P-type silicon is about 32 ampere on centimeter square on Kelvin square. The behavior of diode in both reverse and forward voltage, we have two parts, okay? Reverse bias or reverse voltage with V is negative. Diode acts like capacitor. When a diode is reverse biased, the depletion region widens. The depletion region behave like the insulating layer, of a capacitor with P and N sides acting as the plates. The capacitance depends on the width W of the depletion. So region, so C is proportional to 1 over the width, increasing reverse voltage, wider depletion, and smaller capacitance. This is why a CV curve capacitance decreases as a reverse bias increases. So in inverse bias, the diode stores charge, behaving like a voltage-dependent capacitor called junction capacitance or depletion capacitance. But in forward bias, when the voltage is positive, the diode acts like a resistor or a conductor. When the diode is forward biased, depletion region shrinks and charge carrier flow easily. The diode now conducts currents, and its current voltage relation follows this expression. In this condition, the diode behaves somewhat like a nonlinear resistor, small forward voltage and higher forward voltage, the strong current follow. So in forward bias, the diode passes current acting like a resistor but nonlinear curve. As summary, we have the bias condition in reverse or in forward, the behavior if capacitor in reverse and resistor linear in forward, equivalent component, this is like a junction capacitance, here like a conductor. Physical explanation, the depletion region store charge, and the current flow through narrow depletion zone. The film of the diode-based BG thin films. From the thermoionic, we can get some parameters which are important for the study of our device. We can have here ideality factor here versus light power. And in this second y-axis, we have a saturation current. So the ideality factor is given by charge of electron over kT, derivate to the voltage or over the derivative of logarithm of the current. We can see we have a decrease, then an increase, and for the saturation current also we have a decrease, then an increase, then a decrease within this range of light power. In this second graph, we have photocurrent, and the photocurrent is calculated by the difference between light current and dark current at limit values of reverse voltage. We have an increase with an increase of light power. Here we give the photocurrent and photovoltaic parameters. This is the photocurrent versus voltage for 3 intensity levels. And at right, we can give also other parameters like open circuit voltage and short current for the diode, and given by this formula, FF is the fill factor, is the power over VOC times ISC, and we have the increase with the light power for both VOC and ESC. This table gives the results of the photovoltaic parameter of BG on SE, organic heterojunction diode. First column, we have the light given in milliwatts per centimeter squared, 60, 90, and 120. The ESC in microampere, this value, we observe an increase. VOC in millivolt, we observe also an increase. EM is the maximum in nanoampere, a bit increase. Also VM voltage maximum, here an increase also. P max, which times E max times the voltage max. We have this value. Fill factor is still constant. Efficiency, we have this value. So the efficiency is very low. The photocurrent given in microampere, it has these values. And the photosensitivity is the current, photocurrent, over the input's power. We have this value. Here we study the conduction mechanism, the diode. We plot in y-axis the logarithm of current versus logarithm of voltage. We have this for the dark and the three intensities. We observe that we have two regions. Okay, by approximation, linear approximation, we have two regions, and the relation is current proportional to the V to the power m, where the exponent m describes accurately the conduction mechanism. We have here value of m is layer doc, so we have in this range anomic behavior, and in the second region we have the space charge limited current regime in this region. We have parameter here, heterojunction diode determined by the thermoionic emission in dark and light condition. Ideality factor, it's increasing. Barrier height in voltage, Pb, it's also still constant. Saturation current has this value from 144 and decreasing to this value. Some parameters given by another approximation Shank methods in dark and light. We can have ideality factor in dark and also in light. We can have series resistance determined by this expression. We have this value 46 to 81 ohm. We can also determine by another expression using this expression. Here we have 45 to 69 to 81 kilo ohm. Pb in electronvolt, we have these values. Saturation current in nanoampere and rectification ratio, which have these values. So our structure reveals an ideality factor n much than greater than 1. The value too high of n may also result from the effect of insulating layer inserted between the contact and organic layer and strong series resistance. Here we plot the series resistance experimentally versus voltage. We have here this curve which display a peak, and the peak in this is in different frequencies from low frequencies to high frequencies. And here we have plotted the barrier height versus the frequency using this formula, Pb versus the temperature and saturation current. Have an increase. Okay, so the RSV profile describes a peak, and the peak position is removed by frequency towards high voltage, and the peak level decreased with the increase in frequency as displayed by arrow in figure 8. The highest point is recorded at 1.5 kilo ohm and declines gradually with increase in frequency to reach this value. The electric response, we plot for the study of the electric response capacitance versus voltage for this applied frequencies from 100 to 2 megahertz. We have here this curve on the region deep depletion and the region depletion and the accumulation of charge. We can also have some parameters by plotting 1 over C square versus voltage using this formula. And we have this curve for the experimental frequencies. Here we plot the conductance GV plots, the electric parameters versus voltage for the frequencies. We have this curve increasing. And at right, we have density of donors versus the frequencies, and we have also the voltage of diffusion versus the frequencies. This table we displayed some dielectric parameters versus frequencies, density of donors, diffusion voltage, and barrier height. We have these values increasing, here increasing, and here also increasing with frequencies. We can also study the interface state density given by this expression, and we have this curve versus the frequencies given on kilohertz, have a low frequency and high frequency. This sketch of circuits for interface states given by this circuit. The Nyquist plots. The Nyquist plots is a graphical representation of dynamic system frequency response, plotting the real part of the impedance of its transfer function against the imaginary part of a complex plane. Okay, we have plotted here for four frequencies. As a conclusion, BG dyes-based thin films are fabricated by simple low-cost route. The BG on silicon diode is considered by current voltage characteristic under dark and light condition, and CV characteristic at various frequencies. The stricter based on BG uncover an ideality factor N a lot more prominent than 1. The too high estimation of N can likewise be the after effect of the impact of the protecting layer, which is embedded between the contact and the organic layer, and higher series resistance of 70 kilo ohm, a large interface concentration DET. The CV plot and the electric parameters are strongly dependent on frequency. The barrier height obtained by IV matches that CV, and the F peaks present in the GV characteristic show the existence of interface states. The density diminish at high frequency because these states do not follow the signal at high frequency. BG on silicon may contribute to play a role of diode and photodiode. Their properties meet the microelectronics, optoelectronics, and photovoltaic application. Here, some acknowledgement. This work is included in a project. Some reference here. Some most achievement between 2022-2025. This is our some chapter books with Tunisian collaboration, with Indian collaboration. Some also, this is our chapter book. This is the recent paper on curcumin organic and or phthalocyanine green pigment, on also glutathione as photodetector, and on silicon semiconductor insulator silicon heterojection. Thank you for your attention.